In the last video series, we were taking a look at heat transfers and starting to look at some ideal gas processes. To take the analysis further, we're going to now segue into the first law of thermodynamics. And this is really a statement of energy conservation. So we write that the change in thermal energy, we have been using delta E thermal, but I'm changing notation for consistency here, is equal to, of a system, is equal to the heat transferred in minus the work that the system does. And here, signage is very important, and it is not universally agreed upon in the physics community. So let's be careful to go over the signs here. If delta U is positive, that's going to mean that the thermal energy increases. And if delta U is negative, that's going to mean that the thermal energy of the system decreased. Similarly, all heat transfers are always reckoned as inbound. So if Q is positive, that means the system gained heat. And if Q is negative, that's an outbound transfer. That means that the system lost heat. Now, where there's not universal agreement is on the sign for W. Since we're going to be taking a fairly practical focus, we're going to be adopting the signage that's typically, that pretty much all engineers use and is useful if you are being practical in terms of thinking about how much work you can get out of some sort of an engine. So we're going to adopt the convention that positive work means that the system performs work, and that W negative means that the system received work, that work was done on it. And like I say, these are not universally agreed upon. It is very common in many treatments to reverse the signs, to say that positive work means that work was done on the system, and negative work means that the system did work, in order to keep the signs consistent with the signs for heat. We're not adopting that, but you should be aware, because there's a roughly 50-50 split, near as I can tell in books, what you should generally do is flip to the first law of thermodynamics and see whether there's a plus or a minus sign in front of the work. If there's a minus sign, they're using the definition we're using. If there's a plus sign, then that means that they're using the opposite definition, where positive work means that work was done on the system, and negative work means that work was done by the system. Now, so this is a statement of energy conservation. It's just saying that the thermal energy of the system is affected by two possible transfers in from the environment. That'd be either a heat transfer or mechanical work was done on the system. Now, it turns out that in the history of developing the laws of thermodynamics, there were numerous statements, especially the second law, but even of the first, of these principles that seem radically different at the surface. And there's about a 15-20 year period of physicists demonstrating the equivalencies of all of these statements. I'm going to give you one of these statements because I think it's a useful one. So here I'm going to define a perpetual motion machine. Of the first kind. Which, because that's a mouthful, and yes, there is a second kind, and we will be dealing with it, I will usually abbreviate this as PMM1K. A perpetual motion machine is one where the machine, it's some sort of a machine that produces more work than energy put into the system. And the alternate statement of the first law can be written as you cannot build such a machine. Now that seems really, really different from the statement we had before, but not really. If you think about it, if you have a machine that's going to be doing some sort of useful work, that machine ultimately has to run in some sort of a cycle. In other words, it has to do a bunch of things, and then it has to get back to where it started so it can do those things again. So for instance, if you think of a car's engine, it depends on the details of what kind of fuel the engine is burning, but there's typically some sort of a process where you're bringing in a fuel-air mixture, you compress it, you have a spark ignite it, the subsequent explosion has the piston go and do mechanical work to help push the car along, and then you run through a cycle to send the exhaust out into the atmosphere, and then you start all over again by injecting more fuel-air mixture into the engine. So if you didn't run in a cycle, then you're just doing a thing once, and that wouldn't be what we would usually think of as a machine. So if it runs on a cycle, that means it has to eventually come back to where it came from. And getting back to where it started means that the thermal energy of the system has to be the same again, because when it gets back to where it started, it'll be at the same temperature it was before. So, after a car's engine is warmed up, and it gets to putting in that fuel-air mixture each time, the temperature is going to be the same each time. And because the temperature will be the same at that point each time, that means that there's no change in thermal energy. So what that means is that this bit here is 0. And so what we get is that the most work we can get out, most work we can get out would be equal to the heat that gets transferred in. So that's as good as you could possibly do, is to get out what you put in. Now, I'll turn out the second law of thermodynamics will say that you can't even do that good. It's much more tedious to take this in the other direction. It can be done. It's beyond the scope of this presentation to do that. But you'll find as we go along, we'll have many alternate statements of the first and second laws of thermodynamics, and even an alternate statement of the third. And all these statements are absolutely equivalent, even though they sound very different. It's worth knowing them all, though, because it makes it a lot easier to think about systems if you have one of these different equivalent statements in your back pocket. So With that, let's start to think about how much work a gas can do. In a piston. Although it's possible to build thermodynamic engines where the working substance is not some sort of gas, in most practical application, that's probably what we're going to be dealing with. So this is where we're going to spend most of our focus. So let's think about some piston here. So there's the cylinder wall, there's the piston head, and you got a bunch of gas in here at some pressure P. Now, because the piston wall is just sitting here, it's got to be the case that the force due to the pressure on the outside is equal to the force being exerted by the gas from the inside on the piston wall. Now, let's say we go ahead and heat this gas up. For instance, we ignite the fuel-air mixture. Because we heat it up and we're open or exposed, in this case, to the atmosphere, the pressure isn't going to change. So that means that after the power stroke, let's say the piston moved out this far, some distance, delta x. Now the work that the gas did would be equal to the force that the gas exerted times this distance, delta x. But that the force that the gas exerted would be equal to the pressure of the gas times the area of the piston, of the cylinder, delta x. But this area times this distance here is going to be equal to this cross-hatched volume here. This is how much the volume of the cylinder changed when the piston head moved out. So we can say that this is the change in the volume, and so we conclude that the work done by a gas, the useful work that we can extract from a gas will be equal to the pressure of the gas times the change in the volume of whatever cylinder it's in. Okay, so now let's go and think back to our PV diagrams, and now we can start to see why they're so awesome. Let's imagine for the moment that we have an isobaric process, like what I was just modeling here. If we have an isobaric process, I go ahead and make a graph of pressure versus volume. It's going to look like this. So we're at a constant pressure P. This would be my initial volume here. This would be my final volume here. So this difference in distance along the v-axis here would be my delta V. And then I can observe that the area under the curve here is equal to P delta V, which is equal to the work done by the gas. There is a caveat here, and that is that the direction of this arrow matters. The work will be positive if my process runs left to right in PV space. It'll be negative if the process runs right to left in PV space. You think about it, if it runs left to right, that means the volume increased. That means that the piston had to push against a crankshaft or something and is doing work. On the other hand, if we're going right to left, that means the volume is decreasing. That means that the environment is doing something to compress the piston, probably to get ready for the next part of its cycle. So that's for an isobaric process. And you can probably see where this is going. If you have a general process, and the important caveat here is that you have to be able to draw the process. Remember, we're operating under the assumption that everything is operating slowly enough that we always have a well-defined pressure and volume. Although engineers have come up with really cool cheats if that isn't the case. But let's take a look at, say, maybe an isothermal process just to give some flavor for that. So this is the initial point, that's the final point. So here, this would be V initial, there, that would be V final. And it turns out that the work that we get is equal to the area under the curve in general. Now, again, if you happen to have processes that are like nice straight lines or something like that, you can use, you can say, imagine cutting up into boxes and triangles and stuff like that to figure out the area under the curve. In general, you would need to use the methods of calculus, which would be beyond the scope of this presentation. So let's take a look at one more ideal gas process. This is an adiabatic process. In an adiabatic process, there is no heat transfer. We'll compute the work done later, but for now we can describe the process. So here what I'm drawing is I'm drawing a very well insulated piston. So this is all a lot of insulation right here. In order to keep any heat transfer from happening either in or out of the gas. Then what we can imagine is having a stack of coins on top. So let's say we're doing an adiabatic expansion. What you imagine doing is you take one coin off the stack and you wait a while for the system to stabilize. What will happen is that the pressure went down because we reduced the weight of the coins on the piston, so that reduced the pressure on the gas. So the pressure went down and the volume of the gas will end up going up. It turns out that this process, using the methods of calculus, you can show that, say if this is P initial, P final for my adiabatic expansion, V initial, V final, like that, it's going to look something like this, which is not an isotherm. It's actually at a steeper, it's actually a steeper curve. Pressure is going to go, instead of as 1 over the volume, it goes as V to the negative some number gamma. And this number gamma, it's always going to be bigger than 1. So that's why this will run steeper than an isotherm would. But the exact value of gamma depends on the composition of the gas. So that's something that I'll defer as well. Okay. So the big deal here is by the first law, since there is no change, since there's no heat transfer, delta E thermal equals Q minus W work done by the gas. Since the heat transfer is zero, delta U, since the heat transfer is zero, the work that we get out of the change in the thermal energy will be equal to the negative of the work done by the gas. So we have no losses to the environment. This part of a process would have a perfect conversion of thermal energy to work. Okay, so with that in place, we can start to think about heat engines. Now, a heat engine, again, doesn't have to involve a gas as its working substance. So one of the requirements is that the engine have what's called a working substance. Perhaps the best example I can think of a non-gaseous working substance would be the igniter that you see in outdoor barbecues. That has a little piezoelectric crystal in it, and by deforming the crystal, that causes production of electricity to jump a spark to start the igniter. So that's probably about the best example I can think of a heat engine that has a solid as a working substance. But for the most part, these things are going to be gases, so let's just go with that as the typical. So just to give an example of a process, let's imagine I have a piston here, and whoops, there we go. And I have a weight sitting on the piston. All right, so we got some gas in here, and then we go ahead and heat it up. Since it's open to air and we're not changing the weight on here, what will happen is we will have an isobaric expansion that will serve to lift the weight. And then when we get to the top of this, we'll turn off the heater, and then we will stick a pin in here. So from here to here, this is an isobaric expansion. Now we'll insert this pin, and we will take the mass off, and then we'll just sit and let it cool. So this is happening at constant volume. So this would be an isochoric cooling. And then finally, oops, sorry, we still have that pin. Then finally, we'll remove the pin. And when that happens, this is going to slam. We will go ahead and steadily push down on the piston until it ends up back where it started. And since this is not an insulated jacket, it's open to the environment, this would be an isothermal compression. So let's go ahead and draw this in PV space to get some feel for it. So we start here, and then the first step of the process will be going from point 1 to point 2 here. This will be our isobaric expansion. So then in the next step, this is when we have our isochoric cooling. Pressure drops, but the volume stayed the same. Then finally, we returned it along an isotherm from point 3 back to point 1. And now we're ready to stick another mass on, lift the mass, and so forth. So if we follow the heat flows, heat flowed into the system here during the isothermal expansion, and then during both the isochoric cooling and during the isothermal compression, heat left the system. So this heat had to come from somewhere. We'll say it came from a hot reservoir. We'll define that more in a moment. And then the heat had to get rejected to somewhere. We'll say that that was rejected to the cold reservoir. The work that we extract from the system will equal the enclosed area. And the work will be positive if the cycle is running clockwise in PV space, and the work will be negative if it's running counterclockwise in PV space. All right, so this gets us to a point where we can start to draw some heat transfer diagrams and think about the efficiency of our engines. So when we draw a heat transfer diagram, there are conceptually there are three things that we keep track of. So what we call the hot reservoir. And a reservoir is just something from which we can either add or extract heat where we won't change the temperature all that terrible much. And then we'll have here our working substance. Usually draw that as a circle. It's usually going to be our gas. Then we usually draw another rectangle here, labeling that T cold. And this is, you guessed it, the cold reservoir. And conceptually, any practical engine can always be described as some sort of a device that extracts heat from the hot reservoir. Then we extract work from it. If work is being done on it, you draw the arrow coming in from the left. And then it rejects heat to the cold reservoir. And the total amount of heat rejected will be less than the heat extracted if we did useful work. Since we're running in a cycle, the change in thermal energy will be 0. So by the first law, the total heat transfer had to equal the work extracted. So the work extracted will be equal to Q hot, that was the heat coming in, minus Q cold, that was the heat we rejected out. So if we want to define an efficiency for our heat engine, remember all efficiencies are always what you get. over what you had to pay. So here, what did we get? Well, what we get is the work extracted from the working substance, and what we had to pay is Q hot. That the heat coming from the hot reservoir, that's what you had to burn the fuel to get. That's what you had to pay the money for. In the case of a car engine, that's what you are burning some fossil fuel for instance, to get that heat. So the greater the work that you can extract, the better. Now, it turns out, while we're on the subject of doing these energy transfer diagrams, and we'll be revisiting efficiency in the next video when we figure out what the maximum efficiency of something is. But we can extend these energy transfer diagrams to some kind of strange systems. If we think about like our copper rod that we thought about in the previous video series, let's say we heat one end of it with a Bunsen burner, and then we stick an ice cube on the other end. We'll have heat getting transferred from the hot reservoir to the cold reservoir here. So the hot reservoir is the Bunsen burner. It'll be providing Q hot, and then the cold reservoir over here is the ice cube, Q cold. We can draw this as a heat engine, believe it or don't. So T hot, T cold, and our working substance is the copper bar. So here we would write Q hot, Q cold, and that's it. We wouldn't be adding or subtracting any work. So in this case, we could conclude that Q hot equal to Q cold equal to Q. Now it turns out that just because artistically you can draw a diagram doesn't mean that in practice you can draw a diagram. So as an example of a diagram that you can draw artistically but is not allowed in this case by the second law of thermodynamics, so we'll have more on this in a moment, would be if we had our heat transfer from, instead of hot to cold, it was cold to hot. Like that. We could imagine drawing such a thing. But it turns out that the second law of thermodynamics will say that this system is unphysical. And so although you can artistically draw it, it can't happen in practice because this would be a spontaneous transfer of heat from something cold to something hot. Now it turns out you can move heat from something cold to something hot. That happens all the time. That's a refrigerator. But in order to do that, you have to input work into the working substance. So more on that in the next series of videos when we take a look at heat pumps. Now, this is an example of another sort of oddball one we could draw. We could draw Jules Experiment. So remember, Jules Experiment, we converted work entirely into heat. So here you draw hot reservoir, working substance, cold reservoir. Now here you would have work going in, and it would all be rejected as heat to the cold reservoir. And you wouldn't bother drawing in anything connecting the hot reservoir to the working substance. So the hot reservoir didn't actually have to exist, but we just draw it in for completeness sake. Okay, so in the next video we will start to take a look at the second law of thermodynamics to see what limits we can have on the possible efficiency of a heat engine. Catch you in the next one.